Hey everybody, welcome back. I'm going to start off by going through this assignment that I gave you on Tuesday, so hopefully you had a chance to do it. First question is explain why nitrogen oxides are referred to as NOx, and that's because they can be NO2 or NO, which is NO1, but we don't put the 1 on there, so it can be both. So that's why they're referred to as NOx. X is just 1 or 2. Sometimes SO2 can be referred to as SOx. They call them NOx and SOx because it could be SO2 or SO3. So if you see that X, it just means that there's multiple ones of them. Okay, and then in terms of balancing here, so I'll go through this balancing. So we have one carbon, so those carbons are already good. We have 4 hydrogens, we have 2. So if we double it, 2 times 2 is 4. And then we have 2 oxygens from this, and then O2, 2 oxygens. So we have a total of 4 on this side. So 2 times 2 is going to equal 4. Okay. For this one here, we now have 2 carbons, so we have to double this. And we have 6 hydrogens. So if we put a 3 in front, 3 times 2 is 6. 2 times 2 is 4. 3 times 1 is 3. For a total of 7. So we need a number times 2 that's going to equal 7. So you can just put 3.5 there, and that's going to give us 7. And this last one, we have 3 carbons here, so we want 3 carbons here. And we have 8 hydrogens here, so we want 4 times 2 is 8. And then we count up our oxygens. We have 6 from this one, and we have 4 from this one. 3 times 2 is 6, 4 times 1 is 4, for a total of 10. So 5 times 2 is going to get us 10. Okay, so that's balancing. The products of combustion reaction are dependent on the substance being combusted. Explain the meaning of the statement and include an example. So the example that I gave is if we burn coal, which is just solid carbon, and anytime we burn something we need oxygen, well, we would just make CO2. Right, so those would be the products. But if you have that sulfur in there and it combines with the oxygen, we also make SO2. So depending on what you have there, it changes the products. How does combustion lead to global warming? Well, we talked about that. I showed those clouds of CO2. And remember that that certain type of light, ultraviolet light, let me find a purpley one. So this ultraviolet light can go through the clouds and it's absorbed by the ground, and then when it's reflected off again, it's longer and it's infrared, and that infrared gets trapped. It can't go through the CO2 clouds like UV can, so it bounces around and then stays on near the surface of the Earth. So that's how it gets heated up. Number 5, state the type of relationship that exists between the concentration of sulfur dioxide in the atmosphere and the pH of the rain. So when there's sulfur dioxide in the air, it combines with water and it makes H2SO3. So this is acid deposition, right? So the more of this we have, the more acid we have. So more SO2, more acid. But remember, when we have more acid, our pH goes down. Lower pH means more acid. So lower pH if we have more SO2. Name the type of rock that has a high buffering capacity. That's limestone. So limestone is calcium carbonate, and that's limestone. Need to know that. Identify the chemical compound present in this rock. Oh, that's calcium carbonate. And write a chemical equation that shows how the buffer works. So I showed how it's that carbonate ion. It reacts with our acid, and it takes a hydrogen from the acid, and then you end up getting with HCO3 minus and H2O. So it turns H3O plus into H2O, so it gets rid of the acid in solution. Explain the conditions and substances necessary to develop photochemical smog. So there's nitrogen in the air. Most of air is nitrogen, but it doesn't normally combine with oxygen. But it does combine with oxygen if we have heat. So heat from a furnace, heat from a car engine will turn it into NOx, and that NOx is what makes that photochemical smog. List factors that contributed to the occurrence of acid rain in Canada. So burning coal, that's number one. That's the top answer you're going to see. So burning coal. Yeah, honestly, that's like all the answers on the diploma are burning coal. Burning coal is a huge source of acid rain in Canada. So if you know burning coal, you're good. Is acid deposition entirely a resultant of human activity? No, I mentioned volcanoes can contribute to acid rain, but most of it is human activity. And use your knowledge of soil pH to explain how it's possible for soil to be rich in nutrients but unable to support plant growth. So that was that graph that showed what plants or what nutrients are absorbed best in different pHs. So for number 10, the nutrients may be there, but if the soil is too acidic, then those plants aren't going to absorb the nutrients. Okay, and if you're not sure about that one, just take a look at that graph that I showed on the last lesson. 11, explain how mercury biomagnifies in the food chain. So biomagnification is when you have a fish. Let me draw a fish. Perfect. And then we have a seal. That's my seal right there. That's pretty good. So a seal may eat 10 of these fish, right? So if the level's kind of low in this, well, if the seal eats 10, then the level's going to be higher in the seal. And then if we have a polar bear, there we go, polar bear, and the polar bear eats 10 of these, then that concentration level is going to be higher in the polar bear. Don't make fun of my drawings. List of technologies that help reduce SO2. So SO2, you need to know that it's scrubbers. And NOx is catalytic converters in cars. And that was that video that I showed on that. Okay, so that's our assignment. So hopefully that went well. And let's go through some sample diploma questions as well from that. So again, feel free to pause the video so you can do it yourself before I go through and explain it. So to prevent growth of mold and bacteria, winemakers use sulfur dioxide when making wine. Sulfur dioxide in aqueous solution can react to form, that's D. So I'll show that again. So it will combine with, SO2 plus H2O makes H2SO3. Okay, you need to know that. That's acid deposition. Numeric response 5. Conductivity and pH tests are performed on a sample of a buffer solution. So a buffer solution needs to be a weak acid base conjugate pair. Okay, so an example is HCO3 minus is an acid, and its conjugate pair is just going to be missing that H, so CO3 2 minus. Okay, so acids conduct electricity, so 1 is going to be an answer. Acids turn litmus paper blue. Yeah. So we have an acid and a base. Yeah. Sorry. Not a sample of a buffer solution. Sorry. I didn't read the whole question. And the pH of the solution is 5.6. So 5.6 is acidic. So it's going to turn blue litmus paper red. And because it's a buffer solution, if we add an acid, it will maintain pH, that's correct. And also if we add a base, it'll maintain the pH. That's what buffers do. They maintain the pH if an acid or a base are added. So 1, 4, 5, 6 is the correct answer. Acid deposition is most directly linked to. So acid deposition is not linked. I know a lot of you wanted to pick B. Global warming is CO2. Don't pick it. Genetic mutations is UV radiation, which we haven't talked about yet, which is also that one. Metal leaching, that's the number one that acid deposition leads to. So that's when I talked about mercury in the soil and aluminum in the soil. They turn into a liquid in aqueous form, and they get into the drinking water. So which of the lakes above would be most affected by emissions from a coal-fired power plant? So you can see we have limestone deposits, which is a buffer. And granite we don't know about, but granite's not a buffer, right? So granite would be more affected than the limestone because the limestone would stop the SO2 from creating the lakes acidic. So if these guys are out, they would be least affected. And then you can see wind direction here. So the lake that's downwind, which is Lake 2, is going to be most affected because it doesn't have that limestone that buffers. 19, which of the following rows describes the property of ozone in the upper atmosphere and ground level ozone? So upper atmosphere is good. That blocks out UV radiation. But that ground level ozone, that's what contributes to photochemical smog. Okay, so it reacts with the NOx as well and creates more photochemical smog. 20, the environmental impacts that are most directly linked to photochemical smog are, so metal leaching is acid, so that one is out. Increased exposure to UV radiation, that's the ozone layer, which we really haven't talked about that much, and we'll talk more about in our physics unit. Decreased dissolved nutrients in soil. To me, that sounds like acid as well. Increases respiratory infections. Yes, that's what photochemical smog does. Accelerated corrosion of metals. Again, that's acid rain. Increased algal growth in lakes and ponds. That is fertilizer runoff, which we haven't talked about yet. Increased ground levels of ozone contaminants. Yes, ground level ozone and photochemical smog are linked. And decreased oxygen content in lakes and rivers, that's fertilizer again. So 4 and 7 is the correct answer. The main point of this cartoon is that, so you can see that this is that you need to know that winds blow from the west, so they blow east. Prevailing winds carry acid forming emissions away from Alberta and affect environments elsewhere. One major environmental concern related to burning of coal is sulfur dioxide, B. And 18, a major concern associated with the release of CO2 into the atmosphere. CO2 is B, global warming. Okay, so we are going to do a lesson on indicators here, and we're going to try a lab. We'll see how it goes. I'm going to do the lab myself, and then you're going to try to get the answers from the lab. So yeah, we'll see how it goes. We'll try it out. So use a pH meter and or pH paper and indicators to measure the pH solutions. That's what we're going to do. And use indicators and conductivity meter to differentiate between strong and weak acids. Cool. So in your data booklet, you have this chart here, and this tells you about acid-base indicators. So we've already used one acid-base indicator, which is litmus, but litmus is just one of many acid-base indicators. So the columns that you need to know is you need to know the name, that's important. This one here, where it'll change pH and where it'll change color here. So what this first number means is this first number is yellow. So if I am less than 0, which sounds a little bit weird, but you can be -1, well, that's going to be yellow, right? And if I have a pH of 2, well, that means that it's going to be blue. So if I put methyl violet into a solution and it's 2, it's going to turn blue. If I put in a solution of -1, it's going to turn yellow. Right, so let's do another example. So we look at this phenolphthalein here. So phenolphthalein turns from colorless, so let's do an X, to pink. So what this means is that if I put it in a solution that has a pH of 8, it'll be colorless, and if I put it in a solution that's 11, it'll be pink. Okay, the only other thing that you need to know is sometimes you can be in between. So let's look at bromocresol green. So this turns from yellow to blue. So if I put bromocresol green in a solution that was, let's say, 4.5, which is in the middle here, we'll get a little bit of yellow and a little bit of blue. So what's going to happen is it's actually going to turn green, which is kind of cool. Okay. Okay, so I'm going to try out this lab, and I'll post a lab worksheet, and I'll sort of walk you through the first step, and we'll see how it goes, and yeah, we'll try it out. If it doesn't go well, then yeah, whatever. Okay. Okay, so let's give this lab a go. So I'll just go through the design. We're just going to predict the colors of each individual indicators. We'll turn in undrawn samples, drip a few drops of each sample into your spot plate, add an indicator and record the color change. Use the colors of the indicators to determine the pH range for your unknown samples. Okay, so these are the, actually, we're not going to do this one. Delete entire row. We're just going to use 6 to make it easier. So these are our 6 indicators that we're going to use. We have 3 unknown solutions, and we're going to try to find a pH range. So I'm going to do A as an example, and then that'll help you do B and C. Okay, so let's go to my camera. So I have A, B, and C. This is orange 4, methyl orange, methyl red, bromothymol blue, phenolphthalein, and alizane yellow. So what I'm going to do for this lab is I'm just going to do a few drops of A in all of the first columns. And then I'm going to do drops of B, and you can see that they're both clear colorless solutions. Oh no, there's something already in there. That's going to mess up the results. Oops. Someone didn't clean their spot plate well enough. Okay, so now I have all the solutions in there. So now what I'm going to do is just put a drop of orange 4 in all of the top ones. Okay, so you can see 3 different colors that they've turned. And now methyl orange. All pretty similar there. And the middle one's kind of weird, but we'll see. And then bromothymol blue. Interesting. Okay, that's cool. So now we're going to fill in that chart on the Word document here. Oops, wrong one. There we go. So this one looks like, maybe I could do a little split screen here. Yeah. I don't know if that one's right. That's like a brown color. I don't know what's going on there. And this looks like orange. And this looks like yellow. And then this one looks red. This one looks kind of orange. Orange. This one looks pink. This one looks pink too. I know I have that blue in there, but I think it's pink. And this one's yellow. And then bromothymol blue turned yellow. Turned yellow. And then this one turned green for sure. Colorless. Colorless. And colorless. And then the last one looks like they're all yellow, which don't think it's supposed to be that, but we'll just base it on our answers. Yellow. Cool. So I'm going to go through the first one with you here. And what we need to do this is we need our data booklet. So let me open up our data booklet. I should have this open beforehand. Side 30. Where is my data booklet? Okay. I must have deleted it at some point here. That's okay. Sorry guys, just give me 1 second and I will find it because I have an older version on here. This is why you back up your stuff. There it is. Sorry, it's just opening. So how are things going? How's lockdown for you? Still opening. This computer is horribly slow that I'm using at home here. It is loading and certifying pre-flight, certifying scan, and I should have had this ready to go before I started. Why is this so complicated? Okay, here we go. It's totally gonna make me log in now. I don't know what happened there. It just closed down. Oh man. Okay, let me open up the one that I had in. Oh, it's opened again. No, it closed again. This is so complicated. Open file. Yeah, it's making me sign in. I'm just going to open the one that I had. I'm not signing in. Yes, I want to quit. The one we had on our indicators. Yes. Sorry, this is horribly boring. Yeah, this guy right here. Can I get... Oh, nice. I'm just going to make it a little bit smaller. Okay, I apologize for how long that took, but we got it. Okay, so, oh no. Man, this lab is not going well. So we see that our methyl orange should turn from red to yellow. So maybe that like super brownish color was kind of red. Sometimes things don't always work out as they should, but that's okay. Ooh, I have an idea. I'm gonna copy this and paste it. And paste it as a picture. Yeah, we can put it up here. That's good. Okay, good enough. So you can see, so I'm going to do A for you as an example. So A turned brown. I don't know. Sometimes if it turns a weird color, we just sort of ignore that. So I'm just going to ignore that first one. So methyl orange turned red. So if we find methyl orange here, you can see that it turns from red to yellow. That's what it says over here. So the fact that this turned red indicates to me that it's going to be less than 3.2, right? So it's got to be less than 3.2 if it turned red. And then we take a look at our next one, methyl red. Methyl red turns from red to yellow, and it turned a pinkish color. So that's weird again. pinkish might be red. Yeah, so this pink must be red, and if it's red, then it's less than 4.8, but we knew that already because it's less than 3.2. Bromothymol blue should turn yellow, right, which it does. So it turns from yellow to blue, and the fact that we saw our bromothymol blue is yellow means that it is less than 6, but we knew that because it's less than 3.2. Phenolphthalein turned colorless. Well, if it's less than 8.2, it'll be colorless, and alizarin yellow turned yellow because it's less than 10.1. So when going into our lab here, let me open up the lab document again, right? So my pH range is, I know this is less than 3.2, and my main reason that I knew it was less than 3.2 is because the methyl orange turned red, right? That was my biggest indication. Okay, so try those other ones. Go through it for B and C. See if you can get it. I'll go through it tomorrow, and or not tomorrow. This is Thursday's lesson, so I'll go through it after the long weekend, and we'll see how it goes. Okay, and then try to answer these questions to the best of your ability. And if you have any questions, feel free to email me. But yeah, I will go through it on Tuesday. Okay, so have a good long weekend and good luck on this lab. And sorry, that was kind of painful there.